Hello. So, we will continue with our discussion on linear programming. To remind ourselves, let me just quickly run through what we had discussed. The definition of a linear program involves two index sets. One is the set of variables and the other is set of equations or inequalities. This is a matrix of coefficients of conditions, and these are two vectors. The expression that we want to maximize, which is denoted by phi here, is this linear expression where these C0 and Ci's are given in this vector, subject to these equations where xj is supposed to be bj minus aji xi for each j in B. Every variable, those in B as well as in N, are supposed to be non-negative in a solution. In the last lecture, we had described pivoting, which is transferring one variable from N to B and one variable from B to N. So, this is a variable from N, this is a variable from B. And what we did is we chose the J0th equation from the equation set, and this equation should be such that A J0 I0 is non-zero. Okay, the coefficient A J0 I0 is non-zero. We take x I0 on this side and we get x I0. So, the same equation looks like this. And since there was a J0 I0 here, we had to divide the equation by a J0 I0. So, that one equation corresponding to J0 is rewritten here. The remaining equations we wrote this way. All we have done there is that occurrence of x I0 was replaced by the right hand side of this expression. So, we get a new appearance of the same equation, and the same thing we did for the object function. The x I0 was substituted by this expression, and we get this expression for the object function. So, you got to remember that this is a new linear program, but it is completely equivalent to the old one, in the sense that every solution, or rather any variable assignment that satisfies these conditions will satisfy these conditions, and vice versa. Any set of assignments to the variables that satisfies these conditions will do the same here. Now, based on our discussion from the last lecture, we have an algorithm that we are going to describe now, and that is called simplex algorithm. Now, here I am, without mentioning, I am assuming that this algorithm is meaningful only when the basic solution of the linear program is feasible. Recollect that the basic solution is one in which we set all the n variables to 0. So, these are all zeros, these are all zeros, and the b variables, namely xj, are equal to bj. And basic solution is feasible if all these bj's are non-negative, because that is our requirement here. And in the basic solution, the object function takes value C0, because this is gone. Now, subject to this condition that the input linear program has feasible basic solution, we get into this while loop. What we do is we check whether there is some Ci which is positive. If it is positive, if we have at least one such I, then we select such I. Let us say it is I0. So, we have selected an I0 where Ci0 is positive. Now, the next steps are essentially to select a corresponding J naught subject to a condition that we had discussed last time. So, let us just go through that. We initialize a variable delta to infinity. Then the third step says the following: if a j I naught, so for every j we are checking this condition, if this coefficient is positive and if bj by aj I naught is less than delta, then is set delta to that value and j naught to be j. Now, what exactly this step does for us? This step checks out whether there is at least one j such that aj I naught is positive. If all of them are 0 or negative, then this variable delta remains infinite because we never execute this step. If at least one of them is positive, then j naught will be set to that value. Subsequently, if there are several j variables have such that aj I naught is positive, then we are going to select that j naught for which this quantity is the least, and that least value has been set into this delta. Finally, all we are doing is we checking whether delta is infinity. That is to say, we never found any j such that aj I naught is positive. In that case, we return unbounded, else we perform the pivot operation. So, we find the new value of LP to be the old value of LP and we perform pivot with respect to I naught and J naught. Now, let us try to understand what this algorithm is doing. Now, if this while loop terminates, then it will terminate only when all Ci's are less than or equal to 0. Notice that when all Ci's are less than or equal to 0, then the basic solution of that LP in which all Xi's are set to 0 will give me the optimum value of phi. The reason is this is a negative term, and by raising the value of Xi we will never contribute anything positive. So, the best value phi can take is C naught. So, we will output that LP and the basic solution of that LP will be our optimum solution. So, that is one way to terminate here. In case we are in this loop and we come to this stage, we find that delta is infinity. Now, that, as we noticed, happens when for that particular choice of I naught, all j I naught are less than or equal to 0. Yesterday we noticed that when this happens, then xi equal to 0 for all I other than I naught, x I naught equal to infinity. This is, if this assignment we make to the variables of n, then we will still be satisfying the conditions, and the corresponding value of the object function will be also unbounded. Hence, what we notice is that there is a solution with arbitrarily large value of phi or object function. Hence, the solution is unbounded, and once again you can remember that we had seen such a feasibility space in which the solution was supposed to be on this side, and let us say C is pointing in this direction. We can go arbitrarily far, continue to stay in the feasible region and increase the value of the object function. So, that validates the fact that we are outputting unbounded in this case. Hence, the last situation is when neither of these two are happening, then we come to this step. This step says the following, that the Ci naught is positive, the J naught is so selected that two things are happening, that A, the two things happening, A J naught I naught is positive and B J naught by A J naught I naught is less than or equal to B J over A J I naught for all J such that A J I naught is positive. Among those J for which this is positive, this is this J naught is so chosen that this is the least quantity. Now let's take a look again into this expression. That condition guarantees that these are all non-negative. The last condition of the choice of J naught guarantees that this is non-negative. It also guarantees that this is non-negative. Remember that B J naught was, all B J's were non-negative to start with, because we are assuming the input linear program is such that its basic solution is feasible. So all B's, the given B's were positive, non-negative. So this is also non-negative. Hence, the new program that we find has these coefficients non-negative, hence its basic solution is also feasible. And that allows us to continue with this loop, because once again the new LP is such that its basic solution is feasible. One more thing we noticed is that the object function's value for the basic solution can only increase, can never decrease, because this is positive, this is positive, this is positive. Sorry, this is positive, this is non-negative, and this is positive. So it may be 0, but otherwise it can only increase. These are the two ways actually for termination. One is that all these are negative, and second that the solution turns out to be unbounded. But then there is a third possibility. The third possibility is that this while loop which terminates here, remember the while loop terminates here, somehow while loop does not end and this goes into an infinite loop. If it goes into an infinite loop, then we will have a series of linear programs. Let's say we have if their C values, that is the value of the object function in their basic solutions, are, let's say C01, C02, the constant part of the object function are, we know that the maximum value of the object function is bounded, because if it was unbounded it will be captured in this case. Ultimately will freeze, and after that this will never change. Now we have at some point then this thing freezes and it remains the same throughout. If it remains the same, we will have to look at what happens to the corresponding LP from that point onwards. Now in case this thing is fixed, and if we keep record of each LP by simply storing there the BI and NI set, the index sets. then we notice that after a while this set must repeat, because if this is an infinite chain, the set of variables, the union of b's and n is same. It is the same set of variables. In each step, one variable migrates from here to here and one from here back to n. So ultimately, because there are only mod b plus mod n, c mod b possible ways you can partition those variables into these two sets, and their sizes are always same. So ultimately this pair must reoccur somewhere. Now we are claiming that if the pair is the same, then the linear program has to be identical. Now that is not very difficult to see. The reason is that these are all equivalent linear programs, and suppose we have two LP prime and LP double prime which are equivalent, their sets are also same, b and n is same as b and n double prime prime here. If they are same and these are equivalent, then it's not too difficult to see that xj equal to bj prime minus some a prime j I xi, and xj equal to bj double prime minus some a double prime ji xi. We will have these two equations, one in this case and one in the second case. One can take the difference of the two and you end up with the equation. If you take the difference, you are going to get equation to be 0 equal to b prime j minus b double prime j minus some a prime ji minus a double prime ji xi. This equation must be satisfied by every value of xi in the feasible region, because they are equal in for every value of the xi set. Well, this is an equation of half plane, and this equation can be satisfied if it is non-trivial, that is, say, if not all these coefficients are 0. If they are not all 0, then this is a half plane, and that can be 0 only on the plane. Once you get out of the plane, so if you are out of the plane, if you are here or here, this cannot add up to 0. Hence, we know that this is 0 and this is 0 for every value of j. Well, in that case, we conclude that the two linear programs are identical and they are just reoccurring. And if they are reoccurring, then we are not going to gain anything. Hence, we have to locate a point when there are no new programs are occurring. At that time, we can stop. And that linear program, all of these, in fact, all of these give you the same object function. All of them can be given as a solution. We return the linear program as solution. So any one of these are as good as the other. And notice that the two points when we do selection, here for I naught and here for j naught. If we have several j for which delta is same, we can choose any one of them. We must try all possibilities so that every combination is created. Eventually, when you capture that this is not going to change, it has entered into an infinite loop, we can stop and we'll get the solution as any one of these. The point to remember is that the total number of linear programs is only so much. So this loop, the series cannot be longer than this. So we can actually stop after we have found that these many steps have occurred and we have not discovered any new linear program. Okay, so now we are ready to go to the last step of the program, and notice that we had so far discussed the algorithm which works when the initial linear program has a feasible basic solution. But when you are given a linear program, it is possible that the basic solution for that program is not feasible. That does not mean that its solution space is empty or its feasibility space is empty. That is not implied. So now we are going to show how to deal with the case when the initial linear program has an infeasible basic solution. Now let me first, so let me just write down, now assume that initial LP has infeasible basic solution. That simply means that some of the bj's are negative, because if all bj's were positive, then we have a feasible solution, basic solution. Okay, so now we will assume that BL is less than or equal to Bj for all j in B. So BL better be negative. That's based on our assumption. Okay. So now first I am going to introduce a variant of our linear program, and I am going to call it LP auxiliary, LP aux. In this I am going to maximize, I am introducing a new variable x naught which was not present earlier, and I am maximizing minus x naught. This is the only expression subject to this almost the same expression. We have xj equal to bj minus aji I in n xi plus x naught for all j in B, and xk must be non-negative, x naught must be non-negative. Those are kr in n union B. So I have just rewritten the same program. Only thing is I have introduced an x naught in the condition part. I have just added x naught here. But I completely replaced the old object function by this expression, namely minus x naught. And now let's look at this program. First thing I am claiming is that the solution space of auxiliary program is feasible. That is, the feasibility space of LP auxiliary is not empty, and that we can see as follows. All we have to do is give one solution to these conditions, and that is not too difficult. If you take x naught to be minus BL, okay, so the proof is take xi to be 0 for all I in n, and take xl to be minus BL. Notice that BL is negative, so minus BL is positive. XL is positive here, all xi's are 0. And then if you notice, these terms vanish. Bj's are all greater than are greater than BL. So Bj minus BL is non-negative. You are right. Yes. This is for x naught. Yes. X naught is minus BL. and when I plug in minus BL, then this is Bj minus BL, which is non-negative by the choice of index L. Hence, all of these are non-negative. It satisfies all the conditions. Hence, this is a solution, a point inside the feasibility space of LP auxiliary. Second claim we can make is that the optimum solution or optimum value of phi auxiliary is 0 if and only if the original LP has non-empty feasibility space. That is to say, there exists at least one solution which satisfies the condition of LP, if and only if the optimum value of this program is 0. Way to see this condition, this claim is that notice this is minus x naught. So the highest value, and the fact that x naught has to be non-negative, it cannot reach above 0. It can be otherwise, it can be either negative or 0. Now, if this LP has a solution, if any solution, any point which satisfies the condition of this LP, then that will satisfy this condition with x not equal to 0. Will satisfy these conditions. By taking x not equal to 0, you append the solution of this with x not equal to 0, we see that these conditions are satisfied and the value of this is 0. And that has to be optimum solution of this. Conversely, if the optimum solution of this gives me this value to be 0, that means it is giving me x not equal to 0. Hence, we have values of xj's which are non-negative while x naught is 0, because the solution of this will automatically become a solution of this. If we just drop x naught term, because that is taking value 0 in the optimal solution. Hence, what we have found is there is a relation between the optimum solution's value of the auxiliary program and the linear program's feasibility space. We are going to exploit this. Our goal is now to figure out whether the feasibility space is empty, and if not, then we have to find an equivalent program for the original LP in which the basic solution is feasible. Once we get one equivalent form in which basic solution is feasible, we can run the simplex program as described earlier. So now I am going to consider the following transformation. So let's now take LP prime, which is the pivot of LP aux with 0. The index 0 is the index of this variable, and L is that index in B for which BL was the least. So we are going to compute this, and let's write down the expression for this. We are getting max. First, let me write down the condition. We find that x naught looks like minus BL plus XL plus some ALI XI. So this is the equation for XL. We have transformed and brought x naught on this side. The other equations look like xj equal to bj minus bl minus sum eji minus a li xi plus xl for I in n, and our object function was minus x naught, so it should be the minus of this. So it will become bl minus xl minus sum a li xi. This is our pivot, the new program after pivoting about these two coordinates. Now, first of all, let's look at whether the basic solution is feasible or not. So notice that BL was negative and now this term is positive. This is obviously non-negative because BL is the smallest among all the BJs. So both these are non-negative. So we observe that the basic solution of LP prime is feasible. Hence, we can actually run the program. We can run the simplex program starting from LP prime. All right. Now, let LP double prime be the result of running simplex on LP prime. What we had observed earlier is that LP auxiliary has a non-empty feasibility space. LP auxiliary is equivalent to LP prime because we have performed one pivoting. Subsequently, we have performed simplex algorithm on that. So this is also equivalent to LP auxiliary. Since the feasibility space is non-empty, we have of course a solution, and furthermore the maximum value is bounded by 0. So it has to provide a solution to us. This is the final LP, and its basic solution is what we have to look at to decide whether its value is 0 or not. So now we have two possibilities. Cases 1, the phi value of LP double prime is not 0. If we find that the object function has non-zero value in LP double prime, this implies phi value of LP auxiliary is not 0 because they are same programs, which implies that feasibility space of LP is empty. So we can stop. This is one of those cases where we have to be on this side of this half space, this side on this half space, this side on this half space. There is no region where they coincide, all of them. So we can stop here and say that the feasibility space is empty. Now we have to see the case when phi of LP double prime is 0. So now the second case is when the optimum value of the auxiliary program is indeed 0. That is, the object function evaluates to 0. Now, in this case, we know that our original LP, the feasibility space of original LP is not empty. That is what we just saw. So, I have to now give you a program equivalent to LP in which the basic solution is feasible, and hence you can then run simplex program starting from that LP. Now, let us look at LP double prime. What we notice is that LP double prime is the last form when we ran simplex program on this, and we notice that in this case, when we start with a program which has feasible basic solution, every subsequent program has feasible basic solution. Hence, LP double prime. Hence, so we notice that the basic solution of LP double prime is feasible. Because it is coming from here. Now, this is feasible. Now, let us just look at for a moment what is the relationship between the LP double prime and LP auxiliary. What we noticed is that from LP auxiliary, a series of transformations led to the pivoting transformations led to LP double prime. Hence, the two problems are equivalent, and hence their solutions are same. Now, we know that the only solutions which are optimum have x0 equal to 0. So, the optimum solutions have x not equal to 0, and hence the same is true for LP double prime. Now, the optimum solution of LP double prime is its basic solution. So, in the basic solution of LP double prime, so in the basic solution of LP double prime, x naught must be 0. Now, there are two possibilities. One is that x naught belongs to n, or it belongs to the set B of variables. So, this is fine with us. Let us just take a look at this case. In this case, there must be an equation in LP double prime which looks like x naught equal to b plus sum a 0I xi, okay, I belonging to n, of course. This in the basic solution turns out to be 0, okay. So, and b is non-negative, we can say b naught. So, there must be some, there exists some I such that a 0I is negative, okay. Now, in this situation, I can perform one transformation where we swap xi and x naught, and that will be xi equal to b over minus a naught I plus x 0 divided by a 0I plus sum a 0j, j not other than I, rather divided by minus a naught I xi, a naught j this solution has one property, that since in the optimum x naught was 0, then again the basic solution after this transformation is still the optimal solution of LP double prime. And in this case x naught is actually a member of n set, because it has come on the other side of the equality. So in uniform situation, we will assume that LP double prime has x naught in n, because if it is not in n, I can always make this transformation and we end up having x naught in n, and the basic solution, which is feasible, gives you the optimum solution of LP ox. Okay. LP double prime, by forcing x naught to 0 with LP. Notice that in the basic solution x naught is 0. We can now set x naught to 0 and leave all the other variables as it is. In our auxiliary program, if I force x naught to 0, this program reduces to the original LP as far as the condition part is concerned. So what we notice is that the conditions of LP double prime with x naught forced to 0 is equal to condition of LP. They are same. But the advantage is that LP double prime had feasible basic solution. Then this also must have feasible basic solution, because the basic solution of this had x not equal to 0. So all the other variables values will constitute the basic solution of this program. Okay. So observe that the basic solution of LP double prime with x naught restricted to 0 is feasible. Okay, you notice that the basic solution we can actually give by taking the basic solution of LP double prime and just dropping x naught, because there was x naught 0 there. So we are anyway removing it. That constitutes. So what we have here, as far as the conditions are concerned, they are equivalent to LP, and the basic solution of this is feasible. That is all that matters. The object function does not play any role in this part. So now we are ready with a new program, LP new, in which we'll start with our original expression phi to be C0 plus some Ci xi, I belonging to n, and the conditions will be replaced by LP double prime restricted to x naught equal to 0. There's only one thing that you may have to do, is that the n and b sets of this may no longer be the same as the original one. So for all those variables of n, old n, which are in b set of this, we can plug in those values for this. Just plug in those values, because you will have, suppose I, a particular I naught in n is in b set of this, then there will be an equation for x I naught here. We plug in those values. So we will suitably transform this with respect to the new set of variables, and now we are ready with a new program which is completely equivalent to the original LP. But the advantage of this program is that its basic solution is feasible. And since it is feasible, now at this point we'll begin with simplex program using this program and not this program. This ends the entire algorithm. This is where we stop, because now we have completely described all possible way outs for starting from any linear program. We have seen all possibilities, and every possibility has been taken care of in the complete program.